The second specific thing we can do is find average values of things that we can observe. And so I'll rewrite this equation that the expectation value of an observable S is given by the integral over all space of something looks a lot like the probability distribution, but we have the operator for S sandwiched in the middle. And I'll do this just in one dimension. We'll imagine we just have X. We'll get to other dimensions in the future, don't worry. Okay, and so let's look at an example. Let's say, okay, well, what's the average energy of our system? This will end up being a fairly trivial example if we use the Hamiltonian operator. Okay, so we'll have the integral from 0 to a. We'll look specifically at particle in a box. We'll just write this generically with any old wave function, any value of n. And we'll have the Hamiltonian operator. We won't even write out the whole thing because what we'll see here is that right here, this is basically the left-hand side of the short-order equation. That if we have the Hamiltonian operator operating on our eigenfunction, we know that we defined this. H psi equals E psi, right? This is the Schrodinger equation. And so we can say that this integral will just be integral from 0 to a psi star n en psi n dx. And the energy is just a value, integral from 0 to a psi n star psi n dx. But by definition, this here is equal to 1 because this is our normalization integral that we had earlier. This is the probability distribution. Now that we don't have that operator in the middle, it is simply the probability distribution. And if we integrate over all the box, it has to be equal to 1. And so our average value is just what we'd expect. It's the energy. And so this shows that the expectation value that you get from something that, if you use an operator that is where the wave functions are eigenfunctions of that operator, you'll just get back the eigenvalue. We don't even have to go through. We could put in all the specifics of what H is and the wave functions. We'd get the same result. This is just a simpler way of looking at this. But what's useful about expectation values is that we can do this for things where we don't know the answer already. All right, so we kind of already knew what the answers were for the energies. But let's look at something that more interesting. Let's look at the momentum operator. Now this is not, the wave functions are not eigenfunctions of the momentum operator. And so this will let us calculate P of x, what our average value, our expected value for the momentum is. Okay, so the average value is given by integral from 0 to a. And we'll go ahead and put in our actual wave functions here. And we'll do this generically for any value of n, sine n pi x over a. And then we'll have our negative I h bar derivative with respect to x. So that's our momentum operator. And then our wave function again. Okay, so now we have some work to do here. So the negative I h bar, that will just come out. That's just a constant. But we do need to actually do this derivative here. So the derivative of sine is cosine. And so we end up with the integral from 0 to a of sine n pi x over a times cosine n pi x over a dx. We can look this up in an integral table. And so what we'll see if we do that is that the integral of sine bx cosine bx is equal to 1 over 2b cosine squared bx plus a constant. So we can go ahead and plug in our specifics here, right? So our b here is going to be equal to n pi over a. So we end up with negative 2n pi h bar I, right? So our I h bar gets carried along over a squared times negative 1 over 2 n pi over a cosine squared n pi a over a minus negative 1 over 2 n pi over a cosine squared of 0. All right, I'll go ahead and scroll over here to give myself a little bit more space. And so if we take that, we'll get negative 2 n pi h bar, that's an n, times I over a squared minus a over 2 n pi times 1 plus a over 2 n pi times 0. So cosine squared, oh, sorry, not 0. Right? So we get cosine squared of n times pi, which is always equal to 1, and cosine squared of 0, which is always equal to 1. And so these two terms cancel each other out, and our expected value for the momentum is 0. We went through all that work just to get 0 as our final answer. But as we finish up this video, I want to ask you, does that make sense? So does it make physical sense that we would get 0? I want you to pause and think about that for a second. And the answer is yes, it makes sense. Well, at least I hope it does. Because it's just as likely, right? The momentum in the x direction tells you sort of the mass doesn't change, but velocity, right? Is the particle moving to the left or to the right? On average, it's not moving either way, right? On average, the particle can't leave the box, so it's not moving in a net positive direction or negative direction. It averages out to 0 over time. Now, of course, at any given time, it will be moving to the left or to the right. But if you average out over all, a long period of time, the average is going to be 0. So this is an example of how we can find expected values, average values for things that are not, observables that we can't, that we don't have, accurate information on from the eigenvalue equation.